I'd like to introduce Alexandra Huides, who will be presenting Architect and Build IPv6 Networks on AWS. Alexandra is a Principal Networking Specialist Solutions Architect within Strategic Accounts at Amazon Web Services. She focuses on helping customers build and develop networking architectures for highly scalable and resilient AWS environments. Alex is also a public speaker for AWS and is helping customers adopt IPv6. Welcome to the stage, Alex.
Thank you so much. Thank you. Awesome. Well, thank you folks for joining us and me on stage today for the last session of the day. It's the last session before we all head off to happy hour, so please bear with me. We're going to be quick. Looking forward to your questions and feedback, so please share it in the chat or come to the mic at the end of the session. Also, I have some really cool stickers. So if you stick to the end of the session, you can come here and get the IPv6 stickers from AWS. That being said, let's start with why to start the adoption journey of IPv6 on AWS. And we've quoted 4 reasons, and some of them actually relate to some of the conversations earlier today. You'll see in a second why I'm saying that. But more or less, they summarize into improved network scalability, start building experience. It's a journey, as Corey mentioned, right? It's been here for a long time. We're not there yet. To get there, right, we have to all learn how to use it, what the technical aspects of it are. So it's really easy to do that on AWS. Minimize NAT, both public and private, really important, and simplify global connectivity. And let's dive deeper into each and every one of these reasons. So why improve network scalability? Well, simply you have more IP addresses. Public IPv4 exhaustion is not the only problem we actually deal with. Large-scale enterprises deal with private IPv4 exhaustion as well. Second, subnetting challenges. You folks saw Corey's example in the keynote with creating /24s and then not being able to make them bigger if you need more addresses. Well, good news, in IPv6, that's not a challenge. You can play around with IPv6 only deployments. It is really easy to deploy and test. How many of you folks here have created a VPC? Awesome. How many of you have added an IPv6 prefix to that VPC? Awesome. Oh my gosh, I love how many hands are raised. Awesome. It's also easy to build backwards compatibility. Not all things on AWS or on the internet support IPv6 today. It's a journey, right? But that backwards compatibility is there, and we'll dive a bit deeper into it in a minute. And you can start with the use cases that bring value to your enterprise. A lot of the times we hear from customers the fact that it's really hard to justify why put the effort and the time and the money and the resources into adopting IPv6. Well, you can start by addressing those low-hanging fruits, the cost optimization opportunities by adopting IPv6. Next, no need for public NAT, no need for private NAT. What you will need, though, is for that backwards compatibility, NAT 6.4. NAT 6.4 is also a function of how much IPv6 is supported across all your infrastructure, across all the services, across the internet. So the more IPv6 is supported, the less NAT 6.4 you're going to be using. And last but not least, no more overlapping IPs. I work with AWS customers every day on network architectures, and I think most of the conversations start with, so I have all these overlapping IPs because my developers started their projects on AWS, and they did not think about going back to the network team and actually asking for some IP addresses. That's not a problem anymore. Also, the overlapping IP is not necessarily coming from the fact that developers not knowing overlap IPs, but also from mergers and acquisitions. And this is one of the reasons that customers have identified that there's a challenge in integrating mergers and acquisitions. right? So really important. And last but not least, summarization and efficient routing. Really important. It's really easy to summarize in IPv6. It matters how you're starting. So we'll see the addressing plan capabilities in a second. And you can build those efficient addressing schemes with IPv6. Now, what are the approaches for adoption? Well, so two main ones on AWS, which are really close to how IPv6 is adopted also in traditional networks in the data center, right? Outside in and inside out. What this means, and we're going to dive a bit deeper into, is you either start at the edge with your services, services layer exposed to the internet, or you start internal first. These two adoption strategies are, adoption approaches are also complementary. So you don't have to say, oh, I'm starting outside in, but I cannot do anything on the inside of the network, right? It's very important, complementary. Outside in means starting at the services layer, continuing with the Amazon VPC services, VPC connectivity, and on AWS and hybrid. There's a couple of benefits to this adoption. First is IPv6 enabled end client experience. So no CGNAT in the service provider networks for IPv6 clients. Expanded user base in geographies with high IPv6 adoption, and of course, contributing to overall internet IPv6 adoption. We have also some really interesting customer testimonials, and I would encourage you to scan the QR codes and go onto the AWS IPv6 website and read more about how our customers are adopting IPv6. On the inside, if we're starting inside out and we're starting to address those use cases for internal network, we're going to see in a second what those are. We start with VPC connectivity, internally private connectivity, VPC services, and services layers. So dual stack endpoints at the edge. Now, a couple of benefits to this one as well, and you're going to see that there's a bit of overlap between the two. So really important. Complementary, again, I'll keep repeating that. Adopting IPv6 internally first helps you address those use cases where private IPv4 exhaustion is really, really acute. So you can unlock scale for container deployments. Containers have been the reason why private IPv4 addresses have started being exhausted. You don't have to be an extremely large hyperscale customer to actually get to this problem. Scale internet connectivity, accelerate the integration of mergers and acquisitions. We talked about this, and build familiarity with IPv6, which is really, really important, right? We weren't born knowing IPv6. We've been so long in the IPv4 world that learning this new protocol takes time. Also, you don't have to be Netflix to do IPv6, but Netflix does do IPv6. There are partners in the space, and they work together with us in developing features and functionalities. So go read more about their adoption journey. It's not just them. We have more customer stories and more customer journeys, and we're trying to bring all of these closer to everyone who's interested in. So scan the QR codes, follow the AWS pages, and you'll find more stories there. Now, what are the focus areas? And the reason why I'm starting with the focus areas is because before we get to the actual nitty-gritty details and technical information, we have received from customers, we're working backwards from customers, and we received from customers the feedback of, how do I approach this? This is a new thing, right? We've been at it for 20 years or so, more than 20 years. How do I get started? What should I be focusing on? How should I take the structure of my organization and try to map it to this adoption journey? And we've identified 4 areas. the network, operating system, application code, and services and tools. And we can work together with our customers exactly on these areas, and they map really good with how organizations are structured as well. Now, at each and every one of these adoption-focused areas, there's a lot of things to unpack, right? There's a lot of technical challenges. There's a lot of technical learning to do, right? There's a lot of dependency discovery, right? So where do we start? Well, first and foremost, we start with addressing, right? And this is the main area of focus, because we have an opportunity of starting clean with IPv6, right? And there's two interconnected concepts on AWS, and not just on AWS actually, generically in all networks. First is the addressing plan. And how do we think about it? How many regions do we have? How many data centers? How many virtual private clouds we have? And the addressing capabilities of each of these components, right, in our network. How big should the size of the addressing plan should be for a certain area, right? And starting from here, there's a couple of capabilities that will help you start with IPv6 on AWS really easily. The first one is you can, if you don't own IPv6 addresses, you can get IPv6 addresses from AWS assigned with your VPC. They're VPC level provided global unicast addresses. Let's dive a bit deeper into these. By default, the prefix size is a /56. It is Amazon provided, so it is taken from Amazon pools of IPv6 addresses. This is the default prefix size. You can create new VPCs and you can add IPv6 to them. You will see there that you do have to have a v4 CIDR, and we're going to talk about that in a second. You can also retrofit existing VPCs, right? So you have your VPCs created. You can go and you can add an IPv6 prefix to that VPC. You can add up to 5 prefixes to a VPC without any issues. And you will see that the v6 CIDRs can be also added and removed. They're not primary CIDRs on the VPC. The IPv4 one is. Now, from these CIDRs that you associate with your VPC, you create subnets. Now, you can have a mix of subnets in your VPC. And I've received this question a lot of times as to, well, now that I've added IPv6 to my VPC, do I have to put everything in my VPC on IPv6? Will it have everything that I have in my VPC? Will it have an IPv6 address? The answer is no. Only what you decide will have an IPv6 address will get an IPv6 address, right? So it's a really safe process to adopt IPv6. And you can have a mix of subnet types, right? We're going to dive deeper into this one as well. Also, if /56, which is the default size, is not something that you can work with and you need different sizes of the CIDR, you can have on a VPC between a /44 and a /60. Best practice here, though, is to think and understand why, right? What are the drivers behind not sticking to the defaults? And drivers may be architecture, may be addressing limitations, depends, right? But as long as you understand what the drivers are, you'll be able to make the right decision. Also, not just from the perspective of the Amazon provided GUA, but also from the other options that you have available, which we'll dive deep in a second. So the CIDR of the VPC can be between /44 and /60. The subnets can be between /44 and /64. Not smaller than /64. Really important, because the way the RFC is built with the network portion and the address portion, the network identifier is really, really important to meet. Now, challenge number 1. The Amazon provided IPv6 prefixes are randomly assigned by default, right? So if you have a VPC and you play with it and you test it, that's great. If you have more than one VPC, right, and you're planning on expanding your network on AWS, Having randomly assigned prefixes might not be the best idea because you will actually have a challenge in summarizing. So you can use Amazon-provided contiguous GUA prefixes. Still, you don't have to have your own IPv6 addresses, right? The way you can do this is by using Amazon VPC IPAM, which is the AWS IPAM service. You can create in the public scope of IPAM a top-level pool, and in this top-level pool, you can create or you can receive from AWS an Amazon assigned prefix, size /40 to /52. You can also get multiple of these if you have more resources and you want to expand your network. And from these, you can create multiple VPCs at each region level. So this is a regional addressing plan. Now, you can use this feature in IPAM both in free tier and in advanced tier. So in free tier, you are bounded by an account in a region. In advanced tier, you can get global IP management on AWS across all AWS regions and across all your accounts in the organization. So simplified central management. Oh, clicker. Okay. But Amazon provided is not always the answer to all customer needs, right? A lot of you folks have your own IPv6 addresses and you want to use your own IPv6 addresses. So bring your own IPv6 is also possible. And you have two options, again. The first one is in Amazon EC2, Elastic Compute Cloud. You can bring directly your IPv6 prefixes in an account in a region, and you can address your VPCs there. Or again, you can integrate with VPC IPAM, which allows you to scale this management again, right, across multiple VPCs, across multiple accounts, across multiple AWS regions. Keep in mind that a /48 is the minimal size that can be advertised to the internet. So when you bring your prefixes, even if at the beginning you're thinking, I don't think I'll ever advertise them, right? Never say never, right? Keep in mind that your architecture may change, right? And if in 6 months from now or in a year from now, you're going to say, well, I actually want to advertise these prefixes. What can I do? If your block is a /52, for example, or a /50, we won't be able to advertise it, right? No one will accept it actually on the internet. So keep that in mind. Really important is you have full flexibility when you bring your prefixes to IPAM to advertise them or not, right? So as long as you set them of the correct length and the correct pool properties, really, really important. Those /48s or the top level prefix, you can control if it's advertised, if it's not advertised, right? So you have ownership of that, right? And of course, from these regional pools, you create Amazon VPCs. I didn't mention, but Amazon VPCs are regional constructs, right? So in each region, you will have your VPCs. Now, really important summary. You may think, okay, well, I have so many options. What should I do? This table summarizes that. And the most important thing is think about summarization. Think about how you want internet access to be, right? If you want internet access from AWS, if you want internet access from your on-premises, that's totally fine and possible. You just need to know if you need to have that control over the prefix or not. Cool, so we've done IP addressing, right? We've created the plan, we've thought through it, we've put pen to paper. Now, where do we start with actually adopting IPv6, right? And we're gonna start inside out. And we're gonna start inside out with the Amazon VPC, which is a dual stack construct, right? So to the Amazon VPC, you will add your v6 CIDR, either Amazon provided or from the bring your own IP pool. And Amazon VPC natively supports dual stack routing, so both IPv4 and IPv6 CIDR associated to the VPC are reachable within the VPC. Now, let's take things step by step. First was routing. Second, DNS. Amazon DNS supports natively dual stack, right? So all your workloads in the VPC will be able to resolve DNS queries both for v4 and for v6. What else do we need? Well, subnet types. You have v4 only, dual stack, and v6 only available. So you can test, you can play, you can see which one fits your workload, and you can deploy your workloads in production. Now we have our VPC. We have v6 only as well. So the question that arises is, well, how is that backwards compatibility working, right? What do I need to do for my v6 only subnets to get them backwards compatible with v4? Let's look at a traffic flow. I have my v6 only workload here, and it does a DNS query. The VPC resolver says, okay, cool, I'm receiving this answer, which is a v4 address. But guess what? This workload has nothing to do with that v4 address, right? It cannot use it, right? So in AWS, you have a subnet setting that says, perfect, this is an IPv6 only subnet. I do need backwards compatibility, so the first thing that I need to do is provide DNS 6.4. So DNS 6.4 is a subnet level setting. When you enable it, the Route 53 resolver, when it receives back the actual v4 address, it knows that it cannot send it to the workload. So it synthesizes a v6 address using the well-known 64FF9V prefix. Really easy and straightforward. Now, DNS 6.4 cannot work by itself. And the reason for that is because the actual destination is a v4 only destination, so it wouldn't understand the packet. Now, every single AWS NAT gateway, existing, new, by default has on it enabled the capability of NAT 6.4, which means that it receives the traffic for the well-known prefix, and it's able to create a v4 packet. So it does both source NAT and DNAT. And you're probably going to look at this diagram and say, well, that's a v4 only resource. How is it able to accept an IPv6 packet, right, from the backend? That's the magic that the NAT gateway and NAT 6.4 capability is able to do. So the diagram is correct. It's not a dual stack NAT gateway. We've created backwards compatibility. Now, where does it make sense to actually use IPv6 only in the internal network? And the place where probably you can all agree with me that it makes a lot of sense is to unlock that scalability for container workloads. So Amazon EKS, or Elastic Kubernetes Service, supports IPv6 and supports IPv6 in a way that unlocks that scale. Let's dive a bit deeper into it. So Amazon EKS makes use of worker nodes in the Kubernetes clusters, and the worker nodes have ENIs, or Elastic Network Interfaces. These worker nodes have to be dual stack, right? So they have to have a v4 address and they have to have a v6 address. And they will receive automatically a /80 prefix from the subnet where they're deployed to use this prefix to actually address pods. Really, really important. Pods are actually v6 only. We'll see in a second that they also have that v4 backwards compatibility. So let's look at the pod anatomy. The pod has only a v6 address, and it receives this IPv6 address automatically from the worker node when it gets scheduled. Also, this idea of using /80 as a prefix that is delegated to the worker node helps optimize IPAM-D process, because an API call doesn't have to be created every single time a pod gets scheduled for an IPv6 address, right? The worker nodes know that they have the /80 assigned, so they automatically take IP addresses for the pods from that /80. Now, how is that backwards compatibility being ensured? Well, the VPC CNI for EKS implements a host local CNI plugin where it assigns a host link local prefix. It is a /22. And pods actually get a v4 address from that /22. This actually helps a lot with implementations of service mesh as well. So really, really important. And keep in mind that because it's link local, it's not routable outside of the host, right? So you cannot access it from anywhere outside of the actual worker node. And not advertised outside of the node means that it's not reachable from another VPC or from another host in that VPC. Now let's look at the traffic flow, right, and how this works. You have in the cluster space, in the cluster settings, you have a flag. It's called enable v4 egress. If you enable this flag, the flow will make use of that v4 address, right, the host local. And when it does a DNS query and receives a v4 address, it will use that address to communicate. Now, the services or cluster IP range is from the ULA space. It is an IP space that is reserved, so it cannot be allocated to anything else on the AWS VPC. And you can use this for communication. We're going to see this in a second for communication within a cluster. Also very important, this prefix, the ULA prefix, is not part of the VPC prefix, right? The VPC is a GUA one. Pod to pod on the same worker node communicate using v6. On different worker nodes, also communicate using v6, and v4 traffic is blocked, right? So there's no way that they can communicate using v4 addresses. With endpoints that are v6 capable outside of the cluster, again, it's IPv6 native. This can be in the internal network, and we're going to see connectivity in a second. Very important, DNS queries are the ones that dictate which protocol is going to be used, right? And if it needs to have backwards compatibility to v4 or v6 can be used. And this is really important because you can start, for example, with an EKS cluster that has IPv6 enabled, right? And the rest of your workloads can be v4 because you've just started. Things are not going to break, right? How does internet connectivity work? We are going to talk a bit more in depth about the egress-only internet gateway. So keep it in mind. It provides you private subnet type connectivity to the internet, so egress only allowed and return traffic permitted. And subnets determine the path. Pod to a v4 endpoint, the v4 address is returned to the DNS query, and the worker node performs source NAT on the link local IPv4 address to its own IPv4 address. That's why the worker nodes need to be dual stack. Also, routing to the internet using the same old NAT gateway, you will have another layer of NAT on the NAT gateway. Now, pod to service or cluster IP, again using the IPv6 ULA prefix. And from the services perspective, the EKS clusters integrate natively with the ingress controller with the AWS Elastic Load Balancers. So application load balancers or network load balancers both support dual stack. So you will have your ingress defined by the ingress in EKS. So really, really straightforward. Also, internal load balancers, really important. I've gotten this question a lot, right? Yes, it's v6 addresses, and yes, it's GUA v6 addresses. They are advertised on the internet, but that does not mean that you can actually reach to them from the internet. Every private load balancer, as well as private link endpoint on AWS, have this flag set on them, and this means that there's no way internet traffic can reach to them through the internet gateway. So really, really important. Now, you may ask yourselves, well, backwards compatibility and all, v6 to v4, but how about v4 to v6? You also have this compatibility working with VKS because we do have customers who use pod-to-pod communication, right? And we cannot expect that clusters will be v4 starting a click of a button. So enable v6 egress is another flag that you can set on existing v4 clusters without having to recreate them. And this means that there will be a host local ULA address that is going to be used. Workers need to be dual stack, but the pods will remain v4 and will have also a v6 host local IP address. And this v6 host local IP address is going to be used for connectivity. Now, we have our VPC, we have our clusters, we have our EC2 instances. How do we get connectivity? And this is probably the second thing that comes to mind after you deploy your VPC, right? How do I connect my VPC to different destinations? Well, first is internet connectivity. Who here does the first thing, trying to SSH into your EC2 instances once you've created them? So internet connectivity in IPv6. You have the internet gateway, which is your internet connectivity construct that you can associate to the VPC. At the internet gateway level in IPv4, we make use of elastic IPv4 addresses, so public v4 addresses that are mapped one-to-one to the v4 private addresses in the VPC. So for v4, essentially, one-to-one NAT happens at the internet gateway level. Same as for the dual stack resources in your VPC. On the v4 side, they're going to have a v4 elastic IP address associated to them. And in v6, connectivity is native because of the global unicast addressing capabilities, right? So you don't need to go through NAT. No more NAT. That's good. For IPv6 only, the same occurs for talking bidirectionally with IPv6 endpoints on the internet. And for backwards compatibility, you have that DNS64 piece, and you will go through the NAT gateway for NAT64. Now, for private subnets, by the way, the construct of private subnets and public subnets is determined by the route table configuration. There's nothing more than that. How you configure the route tables is how that subnet is going to behave, either as a public or a private. In IPv4, you have to go through a NAT, right, that allows you to get to the internet. In dual stack subnets is the same construct, so you will still need that NAT gateway for v4, but for v6, to make sure we maintain the same security posture, we have the egress-only internet gateway. And as its name says, right, it's a gateway that allows you to egress to the internet, allows traffic to come back, right, as a response, but it does not allow traffic originated on the internet to reach to your resources, right? In addition to that, you'll have security, and we're going to look at those security constructs in a second. For IPv6 only subnets, again, the egress only internet gateway is your way to go out for private subnets. And backwards compatibility using NAT64. Now, VPC to VPC connectivity. We thought at the beginning that everyone is going to have one VPC. Well, everyone has a lot of VPCs on AWS. It is a good thing, actually. It helps with workload separation and segregation and independent scaling, but it can also be a management complexity, right? How do we connect VPCs? And here comes the challenge of having overlapping IP space. Let's review the connectivity options. So first one is VPC peering. Keep in mind that for dual stack VPCs, in order to be able to peer them, you still have to not overlap the IPv4 CIDR. So VPCs cannot be peered with each other if they're overlapping either in v4 or in v6. And routing over VPC peering is natively dual stack. So if you add the right routes and route tables, you are going to get that connectivity. Now, the second routing construct on AWS is the AWS Transit Gateway. It is a routing hub in a region, and it natively supports both IPv4 and IPv6. When the transit gateway is attached to VPCs, it automatically propagates in its route tables the VPC CIDRs, and at the VPC level, you get to configure routing through the transit gateway. And here is the first place where we see how important summarization is. In the VPC route table, you see that you have a route that says IPv6 summary route, take me to the transit gateway, right? If you wouldn't be able to put that summary route there, you would have to add individual IPv6 CIDRs for every VPC that's connected to the transit gateway. So really a management challenge. Now, if you are expanding across multiple regions in AWS, if you have global connectivity and global segmentation, you can leverage AWS Cloud WAN. And again, native dual stack connectivity. So your VPCs can be dual stack and v4 only. Cloud WAN just routes traffic, right? So it knows about both v4 and v6. Hybrid connectivity, probably the number one use case for customers. Starting with AWS, how do I connect my data centers to AWS? And we have two options here. We have AWS Direct Connect, which is the dedicated connectivity mechanism and option for hybrid connectivity or connectivity to your data centers. Direct Connect has multiple virtual interfaces. So the Direct Connect connection is actually a physical link. It's a dedicated link. And on top of that, you can create these virtual interfaces. We have three types. Here you see public virtual interface that connects you to AWS, and you essentially exchange public prefixes, both on v4 and v6 with AWS. Private virtual interface connects you to individual VPCs through the means of this Direct Connect gateway. Now, both of these virtual interfaces support IPv4 BGP peer and IPv6 BGP peer, right? Over the v4 BGP peer, you exchange v4 routes. Over the v6 one, you exchange the v6 routes. Really, really straightforward, right? Nothing tricky there. Now, if you scale and you have more regions and you have those transit gateways for in-region connectivity, right? You do need the third type of virtual interface, which is the transit virtual interface. Again, v4 and v6, nothing tricky. And as you scale even more and you have more AWS regions and you use or you leverage that global segmentation capabilities, those global segmentation capabilities that AWS Cloud WAN provides, you can, of course, get backwards compatibility with and connectivity with Direct Connect. So here's a diagram that's actually, if you take it and you swap it on the other side so that you don't have to look at it like that, it's really, really common for AWS customers. From the perspective of how do I get connectivity in the cloud? How do I get connectivity to my on-prem data centers? How do I get the network extended, right? And can I do this with v6 as well? And the interesting thing is that we have both types of customers. Or actually three types of customers. We have the customers who've started with IPv6 on AWS, and they're saying, I'm not actually ready to route v6 all the way back into my data center, so I want to keep it on AWS. Really easy here, because you can control what type of peers you have over Direct Connect. And we have the customers who are saying, well, I want to route everything. That's all good. I create all the peers needed, and my infrastructure is going to support v6 way before my workloads actually start supporting v6. And the third type of customer who is really advanced with IPv6 in the data center space. And they're saying, okay, how can I bring IPv6 in my cloud environment? All right, so all three are enabled. And the second connectivity option, if you don't want a direct connection, if you don't want dedicated connectivity, is leveraging site-to-site VPN, so IPsec tunnels. For this, you will have to have two separate tunnels, because each tunnel inside the tunnel can only route one type of, or one address family, right? So you'll have a tunnel for v4 and a tunnel for v6, and the prefixes that you'll advertise are in each of the address families. So pretty straightforward. If you want to scale this connectivity, this is just showing you how that looks like with AWS Cloud One. Now, we've seen inside out, right? We started with EKS, with the Amazon VPC actually, with Kubernetes and containers. We didn't actually have time today to go through all the compute services that support IPv6, but there are many, actually all of them. So go start doing this and start testing and start seeing how it works. And as you do this, you're going to say at some point, well, my use case is actually not internal first. You can have your use case of, I want to dual stack my endpoints at the edge, or I want to minimize my IPv4 footprint at the edge. So let's look at the outside-in adoption strategy. And the first one is, how do I get to expose my services using IPv6, right? Both internally and externally. Internally, there's three mechanisms that you can use. First and foremost, most common and most used by everyone is elastic load balancing, right? Really rarely you're probably going to have a service that is just two EC2 instances. High availability is needed, load balancing is needed, so elastic load balancing is first one. And here you have a couple of flavors of load balancers. Application load balancers, which are layer 7, HTTP, HTTPS, gRPC traffic. They do support dual stack at the front end. To deploy them, you do need to have load balancer subnets. And these elastic network interfaces that the load balancer makes use of are dual stack, right? This is how they can talk to backends that are either v4 or v6, depending on the application capabilities. And this is really, really important. We have spoken to so many customers who've said, well, my applications are not ready to have v6 addresses on their targets, right? It's a legacy application and I don't even know which team maintains the infrastructure for it. You don't have to change the targets. You can keep the targets as v4 and you can dual stack the load balancer at the front end. We've recently launched IPv6 only internet-facing application load balancers. So you will no longer have on these, if you choose to, the A records as elastic IPv4 addresses. This helps optimize that public IPv4 footprint. And the load balancers are actually inside the VPC. Those elastic network interfaces are still dual stack. Because if it would be an IPv6 only load balancer, it wouldn't be able to talk to the backends that are still v4, right? So backwards compatibility is native. The second load balancer type is network load balancer, works at the network layer. So TCP, UDP, TLS listeners, and again, has dual stack load interfaces and either IPv4 or IPv6 targets. The third load balancer type is gateway load balancer. This helps you integrate your appliances on AWS, appliances being either firewalls or whatever other type of layer 3 appliances you have. It makes this integration simple and easy to scale and highly available. And it makes use of gateway load balancer endpoints to attract traffic. So it natively supports both IPv4 and IPv6. And it is acting as a bump in the wire. So the IP destination in the packet is not the IP address of the load balancer. It is the IP address of the target. And traffic is passed through the actual appliances that you deploy for main purposes being inspection. Now, the second one was Amazon VPC Lattice. And this is a new construct that we've developed in terms of application connectivity or application networking. And it's service-oriented. It makes use of developers defining their services, whatever service capabilities those developers have for their services. Each service in Amazon VPC Lattice is dual stack by default. And Amazon VPC Lattice also abstracts completely client and destination IP addresses. So you have v4 clients and v6 targets, or v6 clients and v4 targets, or they have overlapping IP space, doesn't matter, right? Because what the actual client and the service will talk to is VPC lattice IP addresses. Would love to dive deeper into each and every one of these, but we are really short on time today. The third one is AWS Private Link. You're probably familiar with this from consuming AWS services in your VPC or exposing services, SaaS providers that you can consume in your VPC in AWS. It natively supports dual stack, v6 only, depending on the capabilities of both the client and the service. Now, we've talked about connectivity, but let's talk also about security and what the features that are available on AWS to get you to the same level of security that you have with v4, because this is a big challenge. We've heard a lot of customers saying, I don't really know what security I have in v6. These are global unicast addresses. They're routed on the internet. How do I secure them? The first security construct is network access control lists. They're deployed in the VPC. They're associated with subnets, and they natively support both v4 and v6. Subnets are stateless, so keep that in mind. You have to allow both directions, configure them explicitly. The second construct is security groups, which are the firewalls, layer 7 filters around your resources. They're stateful, so they know about connections. Again, they support natively both IPv4 and IPv6 rules. AWS Network Firewall, native firewall capabilities on AWS. You can deploy them, the endpoints for AWS Network Firewall, either in v4 only, dual stack, or v6 only subnets. So you can inspect traffic coming from both IPv4 and IPv6. AWS WAF, so Web Application Filter, and Shield and Shield Advanced protect your edge on AWS. Shield is enabled by default for all AWS customers. Shield Advanced you can enable for your workloads. AWS WAF is natively integrated with load balancers and CloudFront. So really important, they behave the same. They work the same, both for IPv4 and IPv6. Your security posture will be ensured for both of the address families. And last, we've built all the internal deployment. We've built our VPC. We've built our containers, deployments. We've built our services. We've built our internal network connectivity. Let's see how we can scale the internet edge connectivity. And there's two services here, CloudFront and Global Accelerator. So first, CloudFront integrates natively with WAF, is front-ended by Shield, and you can configure Shield Advanced, can target natively load balancers, EC2 instances, S3 buckets, so storage, or custom origins. And it supports, by default, on all CloudFront distributions, both IPv4 and IPv6. It does talk using IPv4 to the origins. I know. And AWS Global Accelerator. This service allows you to route any cast on the global internet to IP addresses per address family, two in IPv4 and two in IPv6, from all the AWS CloudFront Global Accelerator edge locations. So it allows you to attract client traffic as fast as possible on the AWS backbone. Now, it natively supports dual stack, both at the front end and talking to the endpoints, which are either elastic load balancers or EC2 instances. Now, that was a journey. It was a fast-paced journey. So I bet you folks may have a lot of questions. We didn't dive deep into any of these services, but if you want to learn more, probably you're asking yourself, well, what are all the services on AWS that support IPv6? Today, over 30 of them, and we're constantly working on that. And if you're asking yourself, well, this was a great presentation, but it was just like 15 minutes, and how can I embark on this journey after just 15 minutes of attending a talk at the end of the schedule before I got my beers? So if you're interested in all the resources that you have available, please scan that QR code. We're trying to keep that link updated with everything that we publish, blog posts, white papers. We have a workshop there that just got its EKS module in, so you can try all the things we've talked about at EKS. So yeah, scan it out and let us know your feedback as well. That's it. This was it. Thank you so much. Questions? Thank you. No questions. Either everyone is really eager to get to the beers part, or or nothing was clear, or everything was clear. I don't know which way to go with that. No questions. Well, if you folks have any questions after the session, please come find me. Also, if you folks, because you've stayed here until this late hour, please come grab stickers. I'll have also stickers with me, so if you see me around, ask for stickers. They're the pretty cool cat stickers you've seen earlier. So yeah, thank you so much for attending.
Thank you, Alex.